Okay, imagine you're trying to call a friend, but instead of, your phone's contact list, you have this huge old school paper phone book for the whole city.
Right. Massive thing.
Exactly. Now, picture that phone book isn't always quite up to date. People move, change numbers, and the book doesn't catch up right away.
Mm-hmm.
That's kind of the challenge we face with service discovery, especially when you have lots and lots of these small, independent software bits, microservices
Yeah.
that all need to find each other and talk.
It's a good analogy. Each microservice basically needs the current phone number, the network address for any other service it relies on.
Yeah.
And today, we're doing a deep dive into exactly that, how microservices locate one another.
Mhm.
Think of this as essential prep if you're in IT, especially aiming for those senior system design roles.
Right, like a practice session for a technical interview. We'll hit the core concepts, the practical stuff you need to know about service discovery. So our mission for this deep dive is pretty clear. Give you a really solid grasp of the options for service discovery, and just as importantly, how you talk about them effectively in an interview. So where should we start? Maybe the basics, like DNS?
Yeah, DNS, domain name system, that's the logical place to begin. It's fundamental to how the internet works, really. Essentially, it translates those names humans use, like, say, accounts.musiccorp.net,
Easy to remember.
into the numerical IP or Internet of Protocol, addresses that computers actually use to connect. So service A wants to talk to service B. It asks DNS for B's IP address.
Okay. And in a really simple setup, that DNS name could just point straight to one single machine running the service, right?
It could.
But usually, for anything more serious, we point that DNS name to a load balancer instead. And that load balancer then manages multiple copies of the service behind it.
That's the common pattern.
And, when you have different environments, testing, development, staging people often use naming conventions in DNS, like accounts.musiccorp.net for user acceptance testing, and accountsdev.musiccorp.net for dev.
That's a very practical convention, makes things clear. Or, a more advanced way is using totally separate domain name servers for each environment.
Oh, interesting.
Yeah, so looking up accounts.musiccorp.net might give you a different IP depending on if you're on the dev network or the production network. It works well if your network is already segmented like that, but it does add a bit more admin overhead.
Sure, makes sense. The big plus for DNS, though, is it's everywhere, right? It's a standard, everyone supports it.
Absolutely, it's baked into everything.
Here's where it gets tricky. These modern systems, they often have services spinning up and down all the time. Ephemeral hosts, disposable containers.
Very dynamic.
Yeah. Keeping those DNS records perfectly updated in that kind of environment, that's tough. Now, cloud providers like AWS, Amazon Web Services, they have Route 53, which handles this pretty well in their cloud.
It does, yeah. It's quite slick.
But good self-hosted options, historically, they've been harder to come by, though maybe something like Consul could help there. We'll get to that.
We will. And this leads directly to a really key problem with DNS, TTL, time to live.
Ah, TCL, right.
So this key TL value, it tells computers, clients, how long they should remember or cache an IP address they got from DNS.
Okay.
So if you update a DNS record, point it to a new server, clients might still hang on to that old IP address for, minutes, maybe even hours, depending on the TTL value.
Just single phone book problem. They're
Yeah.
calling the old number.
Exactly. And that cached entry could be anywhere, the operating system, middleware, even inside the application itself, like the JVM, the Java virtual machine. It can be tricky to flush out.
Okay, so that sounds like a recipe for failed connections. What's the workaround? You mentioned load balancers earlier.
Right. So the common fix, the pattern you often see illustrated, is to point the DNS record not at the service instance itself, but at the IP address of a load balancer.
Got it.
Then that load balancer keeps track of all the current healthy instances of the service behind it. Maybe an inventory instance A, inventory instance B, inventory instance C.
So the DNS record itself rarely changes.
Exactly. When you deploy a new version or scale up, you just tell the load balancer about the new instance. You don't touch DNS. This avoids the whole TTL caching issue for instance changes.
And the load balancer can also check if an instance is unhealthy and stop sending traffic to it, right?
Precisely. It handles failures gracefully, much more robust.
Okay. And this is way better than that that other DNS thing, round robining.
Oh, yeah. DNS round robining, that's where the DNS server itself just hands out different IP addresses from a list each time someone asks.
Seems simple.
Too simple. It is simple, but problematic. The client gets an IP, but it has no idea if the server at that IP is actually healthy or available. It could easily try connecting to a dead instance. Not recommended for reliability.
Okay, so summing up DNS. Maybe okay for really simple single node things, but once you have multiple instances, point DNS to a load balancer. That seems key.
Yeah, that's the takeaway.
So let's talk more about these load balancers then. You called them a receptionist earlier, which I like.
Yeah, it's a good analogy. The load balancer is the front door, the receptionist. It takes all the incoming calls or requests for a service and then directs them to one of the available staff members or service instances, ideally spreading the workload evenly.
And like we just said, this gives you that even traffic distribution, handles failures because the receptionist knows who's actually at their desk and working,
Right.
and lets you add or remove staff, scale the service without changing the main company phone number, the DNS record.
Exactly. All those benefits come from putting that load balancer in place.
Okay, so load balancers solve the multiple instance problem, and the TTL issue, for instance, changes. But what about really, really dynamic environments where services themselves might appear and disappear frequently? Is a load balancer alone enough then?
That's where things get even more complex and where just DNS and maybe manually configured load balancers start to fall short. In those super fluid environments, you really need something more dynamic. You need a service registry.
A service registry. Okay, what does that do?
It basically performs two main jobs. First, registration. A new service instance starts up, and it needs to announce itself, saying, hey, I'm here. This is my address and port. It registers itself with the registry.
Okay, I'm here.
Second, discovery. Another service needs to talk to that first one, so it asks the registry, where can I find the account service right now? And the registry provides the current up-to-date network locations.
So it's like a live, constantly updated internal directory or GPS system, not a static phone book.
Exactly, a live directory.
And what are some common tools for this? I think I've heard of Zookeeper.
Zookeeper is one of the older, more established players in this space. It actually came out of the Hadoop project. And it's been used for a lot more than just service discovery, configuration management, distributed locks, leader election. It's quite versatile.
Okay.
The key thing about Zookeepers is it's designed as a cluster. Usually you need at least 3 nodes running together for fault tolerance and consistency. It gives you this file system-like structure, a hierarchical namespace, where you can store data.
Like directories and files?
Sort of, yeah. Services can create nodes, put their address information there, update it. Other services can read that information. And importantly, they can set watches.
Watches?
Yeah, they can ask Zookeeper to notify them immediately if the data they care about changes, like if a service's address gets updated. It's also often used just as a general place to store configuration, maybe dynamic log levels or feature flags that you want to change on the fly.
Okay, sounds powerful. But is it the go-to for service discovery today?
That's the crucial point. While it can do it, and has been used for it a lot, the general consensus now is that there are probably better, more purpose-built tools specifically for dynamic service registration and discovery. Zookeeper might be a bit heavyweight or complex for just that task today.
Okay, so maybe avoid Zookeeper just for service discovery if you're starting fresh. What else is there? You mentioned Consul earlier.
Right, Consul. Consul is very popular. Like Zookeeper, it can do configuration management, it has a key value store, and service discovery. But service discovery feels much more like a first-class citizen in Consul.
How does it work?
Well, a big feature is its HTTP API. That's Hypertext Transfer Protocol Application Programming Interface. Makes it easy for services to register and query using simple web requests.
Okay, HTTP, that's easy to work with.
Very. And another killer feature, Consul has a built-in DNS server.
Oh, like DNS again?
Kind of, but smarter for services. It can serve special DNS records called SRV records. That's SRV.
SRV, what's special about them?
They don't just give you the IP address, they also give you the port number for the service.
Ah, because services don't always run on the default web port.
Exactly. So if you have systems that already speak DNS and can handle SRV records, they can often use Consul for discovery almost transparently.
That sounds useful. What else does Consul offer?
Integrated health checks are a big one. Consul can actively check if your registered services are actually alive and responding.
So it knows not to give out the address of a dead service.
Precisely. Now, you might have other monitoring tools doing health checks too, but Consul's built-in checks are tightly integrated with the discovery process. Again, everything registration, querying the key value store, health checks, it's all done via a REST full HTTP API. representational state transfer.
The RESTful HTTP API, so easy integration.
Very easy across different languages and platforms, like registering a user service at, say, 192.168.1.10 on port 8080 might just be a simple HTTP or POST request to the Consul API.
Nice.
And the ecosystem around Consul is strong. There's a tool called Consul Template.
Consul template.
Yeah. It watches Consul for changes like a service address updating, and it can automatically rewrite configuration files based on that new information.
Oh, okay. Why is that useful?
Think about your load balancer configuration. Maybe you use something like HA proxy, that's HA proxy. Instead of manually updating the HA proxy config file every time a back-end service instance changes,
Yeah.
you can have Consul template watch Consul and automatically rewrite and reload the HA proxy config whenever service locations change in Consul. The load balancer itself doesn't even need to know about Consul.
Wow, okay. That is compelling. Automating configuration updates.
It's very powerful.
Yeah.
And there are other integrations too, like with Vault for managing secrets. Consul provides a really solid foundation.
Okay, Consul sounds like a strong contender. What about these big container platforms like Kubernetes? Doesn't that handle this stuff too? Kubernetes.
Absolutely. If you're running your services in containers managed by an orchestrator like Kubernetes, you often get service discovery baked right in.
How does Kubernetes do it?
Kubernetes uses something called etc. That's etcd under the hood. Etc. is another distributed key value store, actually quite similar in concept to Consul Store or Zookeeper. Kubernetes uses etc. to store all its own state.
Okay, so etc. is the backing store. How does the discovery part work for my services?
It's pretty slick, actually. You package your application in containers, group them into pods, and then you define a Kubernetes service. This service acts like a stable front end for a set of pods.
How does the service know which pods?
You use labels, simple key value pairs you attach to your pods, like app.orders. Then you tell the Kubernetes service to target all pods with that label.
Ah, okay. Metadata matching.
Exactly. Kubernetes then gives that service a stable internal DNS name and a virtual IP address. When you connect to that service name or IP, Kubernetes automatically routes your request to one of the healthy matching pods, and it load balances between them.
So if I'm all in on Kubernetes, maybe I don't need Consul.
For many teams, the built-in Kubernetes service discovery is perfectly adequate. It handles the basics very well. You might choose something like Consul if you need its more advanced features, or maybe its key value store, or importantly, if you have a mixed environment.
Mixed, like some stuff in Kubernetes, some stuff outside.
Exactly.
Yeah.
Maybe you have some services running on virtual machines or bare metal alongside your Kubernetes cluster. Consul can provide a single, unified service discovery plane across everything. Kubernetes service discovery is primarily focused within the cluster.
That makes sense. One more option. What about just, rolling your own, using cloud provider tools?
You could. For example, on AWS, you could tag your EC2 instances with metadata like service accounts, environment production, version 154.
Right.
Then you could write scripts or tools that use the AWS API, the application programming interface, to query for instances with specific tags to find their IP addresses. You might even build a little command line tool or a simple UI around it.
Is that a good idea?
Honestly, probably not anymore. It was done more in the past before tools like Consul and Kubernetes became so mature and widespread. You'd essentially be rebuilding a lot of complex functionality, health checking, efficient updates, consistency that these tools already provide robustly. It's usually reinventing the wheel, and likely a less reliable one.
Okay, stick to the established tools then. So we've covered DNS, load balancers, Zookeeper, Consul, Kubernetes. Quite a range. Let's switch gears to interview mode. How would you tackle this question? How would you handle service discovery in a dynamic, containerized environment?
Okay, good question. A strong answer would focus on using a dedicated service registry. Mention Consul by name, or definitely mention the built-in capabilities of the orchestration platform, like Kubernetes.
What key points should you hit?
Emphasize automatic registration services announce themselves. Mention integrated health checks, ensuring you only discover healthy instances. And highlight the dynamic updates. The registry always has the latest locations.
Any tips for answering that?
Yeah, definitely add a caveat. Say the best choice depends on context in the existing infrastructure, what the team already knows, and if you need features beyond basic discovery or discovery across different environments, show you understand the trade-offs.
Okay, good tip. Next interview question. What are the trade-offs between DNS and service registries?
All right, the core trade-off is simplicity and ubiquity versus dynamism and features. DNS, super simple, everyone uses it, it's probably already there. Downside, TTL caching makes it bad for highly dynamic stuff. Updates can be slow or painful.
And registries.
Registries like Consul or etc. give you near real-time updates, health checking, often more features. But they add another piece of infrastructure you need to manage and run reliably.
So it's not always one or the other.
Exactly. A good tip is to mention that DNS pointing to a load balancer can still be perfectly fine for services that aren't hyperdynamic or where instance IPs are stable behind that load balancer. It depends on the specific service's needs.
Makes sense. Final practice question. How do you prevent stale service information?
This directly targets the DNS TTL problem.
Yeah.
So first, explain why DNS can be staled at TTL caching. Then mention the mitigation. Using load balancers so the DNS record itself doesn't change often.
And then contrast with registries.
Yes. Explain that dynamic service registries solve this more directly. They use active health checks and can remove unhealthy or terminated instances almost immediately. So the information you get from the registry is much closer to real time. You could also add a point about client-side caching strategies even when using registries, but generally they are much fresher.
Okay, great. Now, thinking about reliability, what can actually break? What are the failure modes we need to worry about with these systems?
Good point. Everything can fail. With DNS, the obvious one is the DNS server itself going down. No name resolution, big problems. And we've talked about the long PTL causing connections to fail after an IP change.
Right. What about the registries, Consul, etc., Zookeeper?
The biggest risk there is the registry cluster itself failing. That's why they must be run in a resilient multi-node configuration. If the registry is down, services can't register, and clients can't discover services. It's a critical piece of infrastructure.
And network issues.
Yeah. If a service instance can't reach the registry due to network problems, it might get deregistered, even if it's healthy, or new instances might not be able to register. Connectivity is key.
And load balancers. They seem critical, too.
They absolutely are. If your load balancer fails, requests can't reach any of the back-end instances. It becomes a single point of failure unless you've set up high availability for the load balancers themselves, maybe using a pair in an active-passive or active-active setup.
Okay, lots to consider for resilience. This is getting complex. Is there a simple way to structure our thinking when choosing a solution? Maybe a mnemonic?
Yes, mnemonics can help. For the decision process, think DRAFT.
DRAFT. Okay, what's that stand for?
D is for dynamic needs. How often do things really change? R is resilience. How critical is uptime for discovery? Can you tolerate brief delays? A is administration. How easy is setup and ongoing maintenance? F is features. Do you need just discovery or also health checks, key value store, etc.? And T is team skills. What does your team already know and operate well?
DRAFT. Dynamic needs, resilience, administration, features, team skills. That's really helpful for choosing. What about evaluating the mechanisms themselves?
For that, you could use RACE.
RACE.
Resilience, again, how well do they handle failures? Automation, how easy is automatic registration and deregistration? Consistency, does everyone get up-to-date info quickly? And efficiency, what's the performance impact? The resource usage?
RACE. Resilience, automation, consistency, efficiency.
Nice.
And one more. Maybe for the core requirements of service discovery.
How about FRESH?
Okay, FRESH.
Fast updates, reliable health checks, easy configuration, scalable architecture, and H, human readable.
Human readable. That's interesting. We've mostly talked about services, finding services. Why is human readability important?
It's crucial. Because while the services need to find each other automatically via APIs or DNS, we humans need to operate, debug, and understand these systems.
Right, when things go wrong or just to see what's going on.
Exactly, you need visibility. So tools that provide this are really valuable. Consul, for instance, has a built-in web user interface, a UI.
Oh, Ashboard.
Yeah, where you can browse registered services, see their health status, check their tags and metadata, all in your web browser. Very handy for operators.
And Kubernetes has similar things.
Yes, Kubernetes has dashboards and powerful command line tools like kubex control that let you inspect the state of services, pods, endpoints, get that human view of what the system thinks is running where.
And APIs play a role here, too. You mentioned application programming interfaces.
Absolutely. Even for human visibility, having an API for the discovery system is vital. It means you can build your own monitoring dashboards, write scripts to check system status, integrate discovery information into other operational tools, or just programmatically query things during troubleshooting. That programmatic access for humans is just as important as it is for services.
Okay, so don't forget the humans need to see what's happening, too. So let's quickly recap this deep dive. We started with DNS,
Domain name system, yeah.
Yeah.
Simple, standard, but with those TTL caching issues and dynamic setups.
Then we added load balancers as the receptionist to handle multiple instances and mask IP changes.
Right, a big improvement for reliability and scaling.
Then for truly dynamic environments, we looked at service registries. Zookeeper, maybe less ideal now. Consul, very capable with HTTP, DNS SRV, health checks.
And the built-in service discovery and orchestrators like Kubernetes, using etc., which is often sufficient if you're fully inside that ecosystem.
We covered the trade-offs, hit some key interview questions, talked failure modes, and even got some handy mnemonics draft, race fresh.
And emphasize choosing based on your specific context and needs. Understanding why you choose a certain approach is key for those system design discussions.
Definitely. So for you listening, keep thinking about these different scenarios. When would plain DNS suffice? When would you absolutely need Consul or rely on Kubernetes? And why?
And maybe one last thought to leave you with. Considering how fast cloud-native tech is moving, with things like serverless and service mesh becoming more common, how do you think service discovery itself will keep evolving? What are the next challenges we'll face as systems get even more distributed and ephemeral?
Good question to ponder.